Welcome to class. Today we'll be talking about evaluating limits. Often we can just plug in. It's called the direct substitution property. If f is a continuous function, then limit fx when x approaches a is simply fa by plugging in the value of x to be a. Graphically, it shows that if a function is continuous, then there is no hole in the line of fx. So when x approaches a certain value, such as a, the neighboring fx values have to approach the value of fa, as there is no hole. So by using the direct substitution property to calculate the limit for this function, the square root of x minus 1 when x approaches 3, so we simply plug in the value of x equals to 3. So the answer is square root of 2. 3 minus 1 equals to 2. So the direct substitution property makes it pretty straightforward to evaluate limits for continuous functions. We simply plug in the value x is approaching into the function. And the good news is that many common functions we have learned are continuous at every number in their domain. Polynomials, rational functions, trigonometric, exponential, root functions, logarithmic functions, they are all continuous at every number in their domain. So let's do an exercise. What is the limit of this quadratic function as x approaches 1? Now, quadratic functions are polynomials, and polynomials are continuous functions we just talked about. And the domain of polynomials are from negative infinity to positive infinity, the entire real number. Obviously, we can apply the direct substitution property. So we can just plug in the value of 1 to x. So it's pretty straightforward. The answer is 4. Here's a table of the limit laws. It seems like a lot of formulas to memorize, but in fact, they are pretty straightforward. And basically, they allow us to break down complicated functions into simpler ones, so we can evaluate the limits one at a time. For example, if the function is an addition of two functions, fx and gx, then we can evaluate the limit of each function one at a time, and then add the limits together. For subtraction, multiplication, power function, or root function, the same apply. Now, what needs to be careful is that the premise of the limit laws requires the limit for each component function to exist. So if the limit for one of the functions does not exist, either fx or gx, then we cannot apply the limit law by evaluating them separately because one of them, the limit doesn't exist, but treat the original compound function as a whole to evaluate. We'll see some examples to explain that later. First, let's do an exercise. Here we need to evaluate the limit of a complicated function. This function contains an exponential function, a polynomial, trigonometric, and a logarithmic function. But by applying the limit laws, we can evaluate the limit of each component function one at a time. And then by applying the direct substitution property, we can simply plug in the t equals to 0 value and then evaluate each individually and then get the answer. Sometimes plug-in just doesn't work. For instance, in this problem, when we plug in x equals to 2 to the original function, we get 0 over 0 as an answer. Now 0 over 0 doesn't have a definite value, even though we know that 0 over a non-zero constant is 0, and a non-zero constant over 0 is infinity. But 0 over 0 doesn't have a definite value. In calculus, we call this kind of form an indeterminate form. So what do we do if we get an indeterminate form after plugging in? We do factoring. We try to factor both the numerator and the denominator. And then we realize that we have a common factor, x minus 2. By canceling out this common factor, x minus 2, which is also the 0 factor, we can plug in again and get a definite answer. Now 0 over 0 is not the only indeterminate form. Here's the list of indeterminate forms. As you can see, calculus is very different from our common sense. For instance, infinity over infinity, we cannot just cancel out the infinity signs and say the answer is 1. It's not. All the indeterminate forms have their own specific values depending on the particular case, like what kind of infinity is on the top and what kind of infinity is on the bottom and what is the ratio. So we have to evaluate them individually. Later, you'll realize that calculus is all about evaluating indeterminate forms. Here's another example that plug-in doesn't work, because after we plug in x equals to 4, we realize we have a 0 over 0 indeterminate form. But we also realize we cannot factor out either the top or the bottom. So what we need to do here is to multiply a conjugate so that we can go through some algebra and factor out a common factor of 0 minus 4. By canceling out this common factor, which is also the 0 factor, we can plug in again and get the definite answer. Here's a summary of the methods for evaluating limits. The very first thing to do is to plug in. You always plug in and see what happens. If you get a definite answer, then that's it. That's the limit. But if you encounter an indeterminate form, then you need to factor and cancel out the 0 factor and then plug in again. Sometimes the situation is more complicated, like in the last example, where we need to prepare before we can factor and cancel out the 0 factor. There are also additional methods that we're going to cover in other modules by applying the squeeze theorem or by recognizing the limit as a derivative and then use the differentiation formula to evaluate the limit. Here is a very nice poem written by one of my students. I really think she did an excellent job summarizing the methods of evaluating limits step by step. I hope you enjoy it and find it helpful for you to learn this topic. Thank you for watching and happy learning.